Hi guys! Welcome back to Nerd Talk. I am really excited to have you here. So sit back, relax, and get ready for our 10th journey together. This is part 10 of our video series, in which we will discuss about Earth, a planet on which life thrived. Birth of early Earth. Around 4.5 billion years ago, the solar system was still in its early stages of formation. A large rotating disk of gas, dust, and rocky debris surrounded the young sun. This disk contained the raw materials from which all planets would eventually form. Within this chaotic environment, tiny particles continuously collided with one another. Some collisions caused fragmentation, but many allowed particles to stick together due to electrostatic forces and gravity. Over time, these small clusters grew into larger bodies, and as their mass increased, their gravitational pull became stronger. This allowed them to attract even more surrounding material. In one region of this disk, a particularly large accumulation of matter began forming, the early Earth. At this stage, Earth was not a solid planet, but an irregular, growing mass of rock and metal, constantly bombarded by incoming material. Violent accretion phase. The growth of Earth occurred through a process known as accretion, where smaller bodies called planetesimals collided and merged to form larger structures. These collisions were not gentle. They occurred at extremely high velocities, often several kilometers per second. Each impact released tremendous amounts of energy, causing melting and deformation of materials. As Earth grew larger, its gravitational field strengthened, attracting even bigger objects. This led to a chain reaction. Larger impacts caused more heating and further growth. The environment was extremely chaotic, with constant collisions shaping the size, structure, and composition of the planet. This phase was crucial because it determined the bulk composition of Earth, including its metallic and rocky components. Heat generation. The early Earth was incredibly hot, and this heat came from multiple sources. The most significant contributor was the kinetic energy released during collisions. When massive objects struck the Earth, their motion was converted into heat energy, raising the planet's temperature dramatically. In addition to this, radioactive elements such as uranium, thorium, and potassium within the Earth underwent radioactive decay. This process released heat from within, further increasing internal temperatures. As a result, Earth could not cool down during this period. Instead, it became hotter and more unstable, preventing the formation of any permanent solid surface. Fully molten surface. Due to the continuous accumulation of heat, the entire outer layer of Earth melted, forming what is known as a magma ocean. The planet at this stage appeared as a glowing, incandescent sphere, radiating heat into space. There were no oceans, no continents, and no recognizable surface features. The molten state allowed materials to move freely within the planet. Convection currents likely existed within this magma, constantly circulating material between the interior and the surface. This molten condition played a key role in shaping Earth's internal structure in the next stage. Internal differentiation begins. Because the Earth was in a molten state, gravity was able to sort materials based on their density. Heavier elements, especially iron and nickel, began sinking toward the center of the planet. At the same time, lighter elements, such as silicon, oxygen, and aluminum, moved toward the outer regions. This process is called differentiation, and it marked the beginning of Earth's internal organization. Instead of being a uniform mixture, the planet started separating into distinct layers based on composition and density. This separation was essential for the formation of Earth's core and mantle. Formation of core and mantle. As differentiation continued, a dense metallic core formed at the center of Earth, primarily composed of iron and nickel. Surrounding this core was the mantle, made up of silicate rocks that were less dense but still hot and partially molten. This layered structure became the foundation of Earth's geophysical processes. The core would later generate Earth's magnetic field, while the mantle would drive processes like convection and plate tectonics. Even at this early stage, the basic architecture of the planet was being established. Primitive crust formation. As the outermost layer of Earth began to lose heat to space, it started to solidify, forming a thin crust. However, this crust was far from stable. It was constantly being broken, melted, and reformed due to ongoing impacts and internal heat rising from below. This early crust likely existed only temporarily before being destroyed again. It was not like the stable continents we see today, but rather a fragile and short-lived layer floating over a molten interior.
Volcanic activity everywhere. The young Earth was extremely volcanically active. Magma from the interior frequently erupted through the crust, releasing gases trapped within the planet. These gases included water vapor, carbon dioxide, methane, and ammonia. Volcanic eruptions were not isolated events. They were widespread and continuous. This constant outgassing played a crucial role in forming the early atmosphere. Without these volcanic processes, Earth would not have developed the gaseous envelope necessary for later chemical evolution.
The Giant Impact Event. At some point during Earth's formation, a massive collision occurred with a Mars-sized object. This event released an enormous amount of energy, enough to melt much of the Earth's surface once again. The impact also ejected a large amount of debris into space. Over time, this debris came together due to gravity and formed the Moon. This event significantly influenced Earth's rotation, tilt, and future stability. Earth remains unstable. Even after the formation of the Moon, Earth did not immediately become stable. The surface remained extremely hot, with frequent impacts and ongoing volcanic activity. The crust continued to form and break apart repeatedly. At this stage, Earth was still a hostile environment, too hot, too unstable, and too chaotic for life to exist. However, these conditions were essential for setting up the physical and chemical systems that would later make life possible. Intense meteorite bombardment. After its initial formation, Earth entered a period known as the Late Heavy Bombardment. During this time, the young solar system was still filled with leftover debris, asteroids, comets, and rocky fragments. These objects frequently collided with Earth due to its strong gravitational pull. Impacts occurred at extremely high velocities, releasing enormous amounts of energy upon collision. The surface of Earth was constantly under attack, with craters forming everywhere. These impacts were not rare events, they were continuous and shaped the early surface of the planet. Surface reset, again and again. Each major collision had the power to melt large portions of Earth's crust. Some impacts were so intense that they vaporized surface material, turning solid rock back into molten form. Because of this, the surface of Earth never had time to stabilize. Any crust that formed was quickly destroyed by the next impact. This constant resetting meant that Earth remained in a dynamic, ever-changing state, unable to support long-term structures.
Delivery of key ingredients. Although these impacts were destructive, they also played a constructive role. Many meteorites and comets carried water in the form of ice, along with carbon-containing compounds. When these objects collided with Earth, they delivered these essential materials to the surface. Over time, repeated impacts enriched Earth with substances that would later become critical for the origin of life, including simple organic molecules.
Chemical enrichment begins. With each incoming object, Earth accumulated more of the key elements necessary for life: carbon, hydrogen, nitrogen, and oxygen. These elements are the fundamental building blocks of organic chemistry. As they mixed with materials already present on Earth, the chemical diversity of the planet increased. This enrichment created a more complex environment, where a wider range of chemical reactions could occur. Early Earth as a chemical reactor. At this stage, Earth can be thought of as a massive natural laboratory. High temperatures, pressure from impacts, and a mixture of different elements created perfect conditions for chemical reactions. Reactions were not controlled or directed. They occurred randomly, driven by energy from impacts and internal heat. However, over time, these random reactions contributed to increasing chemical complexity. No stable environment yet. Despite the growing chemical richness, the environment remained extremely unstable. Constant bombardment and high temperatures prevented the formation of calm, long-lasting environments like oceans or stable land surfaces. Without stability, complex chemical systems could not persist long enough to develop further. The planet was still in a transitional phase, moving slowly toward more favorable conditions. Foundation for life is building. Even though life had not yet appeared, the essential components required for it were gradually accumulating. Water, carbon compounds, and reactive elements were becoming more abundant. This stage can be seen as preparation. Earth was assembling the raw materials and conditions necessary for the next major step, the emergence of a stable environment where life could begin. Formation of first atmosphere. As Earth's interior remained extremely hot, intense volcanic activity occurred across the entire surface. These volcanoes released large amounts of gases trapped within the planet, including water vapor, carbon dioxide, methane, and ammonia. Over time, these gases accumulated around Earth, forming the first atmosphere. Unlike today's stable atmosphere, this early version was constantly changing, being built and reshaped by ongoing volcanic eruptions. It marked the beginning of Earth having a protective gaseous layer. Composition of early atmosphere. The early atmosphere was rich in gases such as carbon dioxide, methane, ammonia, hydrogen, H2, and large amounts of water vapor. These gases created a chemically active and energy-rich environment. Because oxygen was absent, chemical reactions occurred in a reducing environment, meaning molecules could gain electrons easily. This type of atmosphere is especially important because it supports the formation of organic molecules, the basic building blocks of life. Absence of oxygen. Free oxygen, O2, which is essential for most life today, did not exist in the early atmosphere. Oxygen is highly reactive and tends to break down complex molecules through oxidation. Its absence was actually beneficial at this stage. Without oxygen destroying newly formed compounds, organic molecules could form, accumulate, and become more complex, an important step toward the origin of life. Thick, dense atmosphere. The early atmosphere was much thicker and denser than today's. It was filled with clouds of gases and water vapor, creating a strong greenhouse effect that trapped heat. This was crucial because the young sun was less bright than it is today. Despite that, Earth remained warm enough to eventually support liquid water. The sky would likely have appeared dark, cloudy, and hazy, with very little direct sunlight reaching the surface. Constant volcanic outgassing. Volcanic activity did not stop. It continuously released gases into the atmosphere in a process called outgassing. This ensured that the atmosphere was constantly replenished and evolving. As gases interacted with each other and with the surface, the composition of the atmosphere slowly changed over time. This ongoing process played a key role in shaping Earth's long-term chemical environment. Highly reactive environment. With so many gases present and energy sources like lightning, ultraviolet radiation, and heat, the atmosphere became highly reactive. Molecules frequently collided, broke apart, and recombined into new compounds. These reactions increased chemical complexity, producing a wide variety of molecules. This dynamic and reactive environment was essential for the next stage, where simple molecules would begin forming more complex organic compounds. Gradual cooling of Earth. As millions of years passed, the frequency of massive impacts began to decrease, and Earth slowly started losing heat to space. The surface, which was once completely molten, began cooling enough for more stable, solid regions to form. This cooling was a turning point. For the first time, temperatures dropped into a range where liquid water could exist without instantly evaporating. Without this step, oceans, and ultimately life, would never have formed. Condensation of water vapor. The early atmosphere contained huge amounts of water vapor released from volcanic eruptions.
As the planet cooled, this vapor began to condense into tiny liquid droplets. These droplets gathered to form thick clouds covering much of the planet. This marked a major transition from a gas-dominated atmosphere to one capable of producing liquid water, setting the stage for rainfall.
Beginning of rainfall. Eventually, the clouds became dense enough that water began to fall as rain. At first, when rain hit the still hot surface, it often evaporated quickly and returned to the atmosphere. But as cooling continued, more water remained on the surface instead of evaporating. This marked the beginning of Earth's first true water cycle, with evaporation, condensation, and precipitation happening continuously.
Continuous heavy rains. Rain did not fall for just days or years. It likely continued for extremely long periods, possibly thousands to millions of years. This persistent rainfall gradually filled low-lying areas of the planet. Over time, evaporation could no longer keep up with accumulation. Water began to remain permanently on the surface, leading to the formation of stable bodies of water.
Formation of oceans. As water collected in depressions and basins on the surface, the first oceans began to form. These oceans spread across large portions of Earth, transforming it from a dry, volcanic world into a water-dominated planet. Oceans provided something crucial that had never existed before: a relatively stable environment where molecules could remain, interact, and evolve over long periods.
Nature of early oceans. The early oceans were very different from today's. They were much hotter due to Earth's internal heat and contained high concentrations of dissolved minerals from volcanic activity and rock weathering. They were also slightly acidic and chemically active. These conditions made the oceans ideal environments for chemical reactions, turning them into natural laboratories where complex molecules could begin forming.
Powerful energy sources. Early Earth was filled with powerful energy sources. Lightning storms were frequent in the dense atmosphere. Ultraviolet radiation from the sun was intense due to the absence of an ozone layer, and geothermal heat rose from the planet's interior. These energy sources acted as triggers, providing the energy needed to break chemical bonds and drive reactions that would not occur under normal conditions. Chemical reactions intensify. With abundant energy and a mixture of gases and water, chemical reactions became more frequent and complex. Molecules collided, broke apart, and recombined in new ways. Over time, these repeated reactions increased the diversity of chemical compounds present in the atmosphere and oceans, gradually building a more complex chemical system. Formation of organic molecules. Among the many products of these reactions were simple organic molecules, compounds based on carbon. Carbon is unique because it can form stable bonds with many other elements, allowing the creation of complex structures. These early organic molecules were not alive, but they were essential precursors to life, forming the basic framework for more complex biological molecules. Building blocks of life form. As reactions continued, more complex molecules, such as amino acids, which form proteins, and nucleotides, which form genetic material like RNA and DNA, began to appear. The fact that these molecules could form naturally showed that life's essential components did not require life itself to exist. They could arise purely through chemical processes. Primordial soup develops. Over time, these organic molecules accumulated in the oceans, creating a rich mixture often called the primordial soup. This was not a uniform solution, but a constantly changing mixture of interacting compounds. In this environment, molecules were continuously forming, breaking apart, and recombining. Some combinations were unstable, while others persisted longer, slowly increasing complexity. Transition toward life. As molecular interactions became more complex, certain molecules began to show stability and the ability to interact in more organized ways. Some may have even started forming simple structures or networks. This marked the critical transition point, from random chemistry toward organized systems. The stage was now set for the emergence of protocells, where these molecules would begin forming structures resembling the first living cells. Thanks a lot for watching. If you are liking the videos, please do subscribe, like, and share. And stay tuned for upcoming videos.